You may have heard of gravitational waves before, but the insane difficulty of detecting them, the events that cause them, and the implications they can carry for our understanding of the universe is hard to grasp. Hopefully by the end of this video, you will have a better understanding of the future implications the discovery of gravitational waves will have. Gravitational waves were first theorized by Albert Einstein in 1916 as part of his theory of relativity. Relativity states that spacetime bends around massive objects due to gravity, so gravitational waves are ripples in spacetime that propagate out from moving massive bodies. Similar to how light is transmitted in the form of photons, gravity is theorized to be transmitted by gravitons. According to string theory, these gravitons are strings that are thought to transcend different dimensions, unlike light or matter. However, inside of this universe, all massive objects are constantly exchanging gravitons with all other massive objects in the universe. The gravitons move along the same spacetime continuum as everything else and travel at the speed of light, which is how we can detect them from black holes that collided billions of years ago.
Based on the theory of relativity, all massive objects should create gravitational waves. However, it would take extremely massive objects moving at high speeds to produce gravitational waves strong enough to detect. Events that are big enough to cause these are massive supernova and orbiting binary black holes or neutron stars in the split second before collision. These gravitational waves move at the speed of light and stretch space in one direction and squeeze it in the other as they move through time and space. When Einstein was theorizing gravitational waves, he never thought they would be able to be measured.
On September 14, 2015, the first ever detection of gravitational waves was made. This detection came out of the Laser Interferometer Gravitational Wave Observatory, also known as LIGO. LIGO is made up of two Michelson interferometers located in the states of Washington and Louisiana. The reason there needs to be two redundant systems is because of the sensitivity of the measurements. According to Caltech, LIGO is able to detect changes in the distances of 1/10,000th of the diameter of a proton. Events such as a car driving nearby or slight seismic activity can cause interference that must be accounted for. For the detection to be accurate, the same signature must be seen at both locations at the same time. LIGO works by sending a laser down two perpendicular vacuum chambers that are 4 kilometers long. The beams then hit mirrors and rebound into a photodetector. The recombined light has a particular interference pattern, and if a gravitational wave passes through, one arm of the detector is stretched and the other is squeezed, making the distance the light travels different, which is ultimately detected as a change in the interference pattern.
As of March 2019, 11 detections of gravitational waves have been made. 10 of these detections have been colliding black holes, and the other detection was colliding neutron stars. These detections provide evidence to Einstein's theory of relativity, as well as evidence as to the existence of black holes between the masses of stellar and supermassive black holes. Many more detections are expected to be made in 2019 with LIGO and other similar detectors like Virgo, Kagra, and Geo. These detectors will continue to give insight into the happenings of the universe and its past. An exciting prospect for LIGO and other similar detectors is to try to find gravitational waves that formed during the Big Bang. These could be the key to learning about how the universe we know was formed.